Hello everyone, my name is Rahul. I'm a student of University of Florida. I'm here to present my project presentation titled Comparative Study on LMS, RLS and CMA channel equalization. First of all, I would like to thank Professor Depang Wu for guiding us throughout the whole course. So, I would like to tell my objectives. The main aim of my project is to perform equalization on the three algorithms, which are namely LMS, RLS, and CMA. I have implemented and simulated these models in MATLAB and have compared the performance aspects such as convergence and signal error rate, and I have given a detailed analysis of the three algorithms. So first let us see what is equalization and why is it used. Equalization is used in wireless communication systems to negate the effect of intersymbol interference. So intersymbol interference means overlapping of adjacent symbols over a given time frame. So this happens due to multipath fading, that is due to multiple reflections of the signal and due to the limited bandwidth of the channel. So the equalizer will negate these effects of the channel and will obtain the correct output as the original signal. So we are focusing on an equalizer which is the adaptive equalizer. By the name of it, it suggests that it tracks the signal basing upon the time varying channel. So we'll see how the adaptive equalization works. First, I'll show you the block diagram. So here I of k is the input signal. As it passes through the channel, it gets distorted with the phenomenon of intersymbol interference and spreads its symbols across the m delay elements. So what the equalizer consists of is it's basically a set of m delay elements, each of which have a certain weight. So while we have to select the weight such that the combined product of the channel weight and the input signal gives us the correct output of a signal at the time interval k. So actually due to intersymbol interference, the data at kth interval is spread across the previous time intervals. So we are using the channel weights to obtain the correct output at kth interval. So this happens in an iterative process with the help of some adaptive algorithms that I have mentioned before. So the output of the equalizer at each stage is compared with the signal and the error is calculated and it is used in updating the weights of the equalizer. So basically the function of the equalizer is inverse to that of the channel. It reverses the distortions produced by it. So and after the output is produced by the equalizer, it is passed through the decision maker for quantizing it. So we'll see the types of adaptive equalization. There are basically two types of adaptive equalization. One is channel equalization. So as I mentioned before, equalization works on the concept of updating the weights. So here the weights are updated based on the error and the error is calculated with the help of the difference between the output of the equalizer and a reference signal. This reference signal is obtained from the transmitter and this is usually the original signal. So based upon the error, the weights are updated. So and this process is known as training. So during the training, the weights are updated until the error becomes acceptable. And after the training is over, the equalizer weights are ready. And then the tracking phase comes into place. So the tracking estimates the time varying channel and produces the correct output. And the second type of adaptive equalization is blind channel equalization. The specialty of this equalization is that it requires no training from the transmitter and it depends totally on the input sequence and estimates the channel from it. There are a lot of positive sides and also downside to this type of equalization, which we'll be seeing in the following slides. First, let's see about the first type of algorithm, which comes under the category of traditional channel equalization, that is least mean square. The objective here is to minimize the mean square error. So, as I mentioned before, the channel weights are updated based on the error function, which is multiplied by the input vector that we can see here, wn of n plus 1. So it is manipulated with the help of a single parameter step size. So basing upon the value of step size, the convergence rate can be manipulated. And we'll see the positive side and the negative side to this algorithm. The first, I'll tell about the advantages. It is simple and accurate because it just uses only one parameter to manipulate it, and it is stable to channel noise and interference. And this type of algorithm is good for fast varying channels because it has only one parameter to change and it can adapt quickly. But there are also some downsides to this approach. The first thing is that it has less convergent speed because it has a single parameter. It takes a lot of time to converge. So this may not be desirable in some communication systems. And the second disadvantage is that if the time delay of the signal is large compared to the propagation delay of the equalizer, the equalizer becomes unstable. So we'll see the next type of algorithm, that is the recursive least squares. The disadvantage of LMS we have seen is that it has low convergence speed. So to compensate for the low convergence speed, we are using this type of approach. Uh, Here the main objective is to minimize the least square error. The least square error is the cumulative of all the previous errors and each of which has some weighting factors. Previously we saw that it has only one parameter. Now it has so many weighting factors, so it can converge very quickly. So and this type of algorithm performs more number of operations per iteration. So it is complex. So it has complex circuitry to do it, and the channel weights are updated based on the equation that is stated here. The step size here is made by k of n. So the k of n equation is given here, where R inverse is the input correlation matrix. So yeah, and A is the step size as before. So the tracking ability depends on A. The smaller the value of A, the more accurate this algorithm will be. But the value of A should not be too small, otherwise it becomes unstable. So we'll see about the advantages and disadvantages of this type of approach. Advantages obviously are that it has a very fast conversion speed because it has a lot number of weighting factors, and it has better tracking ability, that is accuracy, and it performs more operations per iteration. Yes. And the disadvantages is that it is more complex because it has to perform more number of operations per iteration. And the second disadvantage is that these type of algorithms tend to be unstable most of the time. Although we can make some changes to it, these changes tend to be a little tricky. So now let's see about the third type of algorithm, which is a constant modulus algorithm. The previous algorithms mentioned before, that is LMS and RLS, come under the category of traditional channel equalization, whereas CMA channel equalization comes under blind channel equalization. That means it requires no training input sequence from the transmitter. So here the error the mean square error is calculated by the difference of the output of the equalizer and a fixed envelope. Previously in LMS, we have received the training sequence. Here a fixed envelope is used as reference signal. In my project, I am using QPSK signal. So I have taken R2 as 2 for QPSK and it is generally 1 for BPSK. So the channel weights are updated in a similar fashion to the least mean square. So the mean square error is multiplied with the output of the equalizer, and these are updated in an iterative process. And let's see about the multimodal property. CMA has this different kind of property. Uh, the cost function that I mentioned before has many local minimas. That means the cost function at any time can select any one of the local minimas instead of the global minima. Sometimes, depending upon the characteristics of the channel, the depth of these minimas can vary widely, and each minima has different delay and different polarities, so different characteristics. So, if the cost function predicts a very uh, low local minima, then it might affect the performance. So we have to take care of this type of this thing by using proper channel initialization. Basically, the output of the CMA equalizer is assumed to consist of two parts. The first part is the actual source symbol, which is assumed to be a non-Gaussian, and the second part will be of multiple access interference from other users, that is the intersymbol interference, which is Gaussian. So we have to select the channel initialization in such a way that the Gaussian output is low, that is the interference is low. So in that way, proper channel initialization can be made. And now the advantages and disadvantages. The obvious advantage is that it requires no training, which is definitely a very good advantage. And since it does not require any training bits from the transmitter, it can efficiently use the bandwidth of the signal for other purposes. And the disadvantages are that it has poor convergence. It has poor convergence than LMS, and it is less accurate compared to the traditional channel equalization. And and the other thing is that we have to be careful of channel initialization, otherwise the errors might not be more accurate. So now I'll explain about the code that I've implemented for the three algorithms. So I've taken a data sample of 3000 points, and I've taken a training sample of 2000 points. I've selected a signal to noise ratio of 25 dB, and I've taken the smoothing length for the channel as 20. During this process, the channel output is smooth. So the values between these intervals are not considered in the calculation, and the channel